Welcome back to AI Verdict, where we strip away the hype and get right to what's actually working in artificial intelligence. Today, we're diving into a pretty wild experiment from a team at Nvidia. Instead of humans writing thousands and thousands of lines of code, they let AI coding agents build an entire deep learning engine from the ground up. They've open sourced it, it's called Vibe Tensor, and you know what? It might just be a blueprint for the future of software. Let's get into it.
And let's be super clear here. We're not talking about some simple demo script. We are talking about a real, functional system, one that manages memory, that handles seriously complex math, runs on GPUs, and can actually train real neural networks. This is a massive, massive leap in complexity from what we've seen AI agents do before.
So, how are we going to break this all down? First, we'll unpack why building these tools is just so incredibly hard in the first place. Then, we'll see how the AI agents took over the driver's seat. We're going to peek under the hood of what the AI actually built, see how it handles the hardware, check its performance report card, and then finally, we'll ask that big question: what does this really mean for the future of software?
All right, so first things first. To really get why this Vibe Tensor project is such a big deal, you have to appreciate the sheer mind-blown difficulty of building the tools we use for AI every single day. It's this whole hidden world of complexity.
This slide just nails it perfectly. As a user, what do you see? A few simple, elegant lines of Python. But underneath the surface, man, it is a massive iceberg. You've got high-performance C++ code, squeezing out every drop of speed. Specialized CUDA code talking directly to the GPU. And entire systems designed just to track millions of mathematical operations. Building this stuff normally takes huge teams years of work.
But Vibe Tensor, well, it completely flipped that script. Instead of a massive team of human engineers painstakingly writing every line, AI agents did the heavy lifting. And that fundamentally changed the entire development process.
So check out this new development cycle. A human starts by setting a really high-level goal, something like, we need a smart GPU memory manager. From there, the AI agents propose and write the actual code. The system then automatically compiles it and runs a battery of tests, comparing the results to a trusted source like PyTorch. If it passes, awesome, the code is accepted. If it fails, it's rejected, and the whole cycle just repeats. The human's role completely shifts from being the coder to being the architect.
Okay, so that's how they built it. The really interesting part is, what did the AI actually manage to put together using this process? Let's take a look at how this thing is structured.
It's pretty incredible. The agents constructed a complete multi-language stack. At the very top, you've got a familiar Python API that looks and feels a lot like PyTorch. Underneath that, there's a C++ core handling memory and execution. And at the very foundation, you've got CUDA code for direct GPU control. It even supports flexible data views, which is a really critical feature for performance that avoids slow, unnecessary data copying. Now, a key component the AI wired up is something called the dispatcher. The best way to think about it is as the system's traffic controller. When you call an operation, like a matrix multiplication, the dispatcher is the piece that figures out where it should run, on the CPU or on the GPU, and routes the request to the right place. It's a perfect example of the system's complexity.
But honestly, this might be the most impressive piece of the whole puzzle, the Autograd engine. This is the heart of what makes a neural network learn. It's the magic. It records every single operation, building a graph. Then, it walks that graph backward to calculate the gradients that tell the model how to get better. The fact that AI agents built this from scratch is a huge, huge deal.
Okay, let's get into the most technically demanding part of this whole system. We're talking about how the AI handled direct, low-level interaction with the GPU. This is where things get really interesting. And the AI didn't just write some simple, basic code. It built a custom CUDA subsystem that actually uses advanced features like streams and graphs to organize work on the GPU more efficiently. It also created a smart memory allocator that intelligently reuses GPU memory to avoid those performance-killing slowdowns. I mean, these are sophisticated, mission-critical systems. So the crucial point here is how they established trust in all this code. The team pretty much replaced line-by-line human code review with automated validation. And when bugs did pop up, and they did, things like GPU kernel crashes, the response wasn't for a human to jump in and debug, it was to add a new targeted regression test and just let the AI iterate until it passed. All right, so the million-dollar question, does it actually work? And what's the catch? Let's dig into the performance data.
The results are a bit of a mixed bag, but in a really fascinating way. Some specialized pieces, like for layer normalization, were actually faster than the reference code. Attention kernels were mixed, but here's the most important part. It was functionally correct. They successfully trained small transformer models, and the learning curves looked just like they do in PyTorch. So yes, it works, but the question is, how well does it work?
Well, that's where we hit the big catch. The authors themselves gave it a very memorable name, a Frankenstein composition effect. And this is really the key to understanding the system's limitations.
So what does that mean? It means that individual components, like a perfectly good arm or leg, could look great in isolation. But when the AI stitched them all together into a single body, these unexpected global bottlenecks started to emerge. For example, a safety lock that was added to the training engine made one component safer, sure, but it also accidentally killed parallelism across the entire system. A locally smart decision became a globally inefficient one, leaving a ton of GPU power just sitting on the table, unused.
So let's be really clear about the final verdict. Vibe Tensor is not a production-ready tool. The code has inconsistent styles, redundant layers, and incomplete APIs, all the classic hallmarks of machine-generated software today. It is a research prototype, but an absolutely incredible proof of concept.
But see, Vibe Tensor isn't trying to beat PyTorch today. That's not the point. Its real significance is what it proves about a potential new future for how we build complex software.
So, what's the bottom line here? First, this is proof positive that AI can generate truly complex, multi-layered system software. It's not just for small scripts anymore. Second, it shows that as AI writes more and more of our code, automated validation becomes absolutely critical. And finally, it gives us this fascinating glimpse of a new workflow, one where humans are the architects, guiding the high-level vision, while AI agents handle the construction.
And all of this leaves us with one final provocative thought. For decades, we have designed programming languages for humans to read and write. But what if the next great programming language isn't designed for humans at all? What if it's optimized specifically for AI agents to build with? That's the kind of future a project like Vibe Tensor asks us to seriously consider. Thanks for joining us on